start again. But you don't seem excited to be around. It's like some of you are still welcoming pressures. You are looking around, who is the CDC? So today is the so those of you who were not there yesterday, we covered the course outline and the video is on wedding. So today we are going to start the course, and in 2 hours I think we shall cover something. I'm kidding, we just tried to do something to be familiar to each other. So those who are coming today, this is my notes are handwritten of these notes seen here almost. I think some of the examples even are the same as the ones in my notes. These notes here are scanned, handwritten here, scanned and put on wedding. I think someone would say, why don't you type them with nice math type equations and the like. I just want to show you that I hustled to write them, and you also have to hustle. They say, I hear and forget, I see and forget, I do and remember. That's my principle. Otherwise, I could type these notes, but someone will say, he just copy-pasted and edited, and he's lazy. I wrote them with my damn hands. Well, maybe also to show you that I have a nice handwriting. What are you going to do? That's my handwriting, in a sense. So, the course is PHY 3112, Electromagnetism. And today I am loaded with everything that I need in order to summarize the course and finish it. And then the rest of the time will be. So I can confirm that I will complain so that next time no one will be here to disturb me in this room, so that we say that my meeting from 10 hours to 12 hours will be here in electronics lab. And then the don't like this square. And then from on today, we run from 15 hours to 17 hours. Do you have any lecture? I haven't said when, you are saying yes. How? Which lecture am I talking about that you are saying yes? So these are the meeting times. I talk the way I talk, and as if we have been almost, because I've been watching my videos of the past. I've been revising this. Electromagnetism. Since I am an artist, it's a designer. Mistake is a design. Yeah. So I have been revising, so I have been watching myself, so that's why it's like I'm back to the days. And I was sharp those days. It's not like these days when I'm a bit growing old. So we'll have hope that man, I don't know, I will try to see whether I can beg that they allow me come here and then have my lecture here. That place, because of being on the road, it disrupts and I hear a lot of background noise in the camera. Previously, I thought people would understand that when I say I capture videos, they would say, we want to get here a nice place so that we see how videos look like so that we can also do it. But it doesn't matter. So, it doesn't matter to others the way it matters to me. So, anyone who has come today that got a complaint on these 2 days, Margaret, it's like school practice wasn't easy. The way you look, the look on your face is like either you are still having memories of the school practice or it was really tough. But that is your issue. I don't want to get into that. But I'm very confident that students showed you touch. They praised you for me. Because I know this was your first school practice. The way you were answering me here. I come here, wait for you, then when I'm complaining about your lecture, you're like, this one, what is he talking about? It's like, now they gave you a dog. And those kids don't give a damn. And if you are lucky and you teach in a private school of the rich people, those kids don't care. They can even chase you. They just tell their dad that guy comes in class and is boasting around. Then they tell the headmaster, that guy is spoiling our children, chasing him. I failed to teach in a private school, in private school because of people thinking I am a babysitter. So one time in one of the schools I was teaching in, I taught, marked, signed the reports. By then my mother was sick in Morocco. I had come to check on her. So as I'm on the way, the door calls. Hello, he was very lousy short man, jumping. Hello, Mr. TWINAMASIKO, yes. Your students are outside here, they are playing. I said, please, I have marked, I have already signed reports, and the term ended, they are waiting for their exams. I'm not a babysitter. That day, we had a briefing. So when I came back, the HM was briefing. She made a joke. She thought I like joking. She said, Mr. TWINAMASIKO was called, and then it's as if he's no longer wanting to be with us. So after her speech, I said, could you prepare me a certificate of either good conduct? Is the way they call it, I've forgotten. Because I'm leaving, and I went to my locker, picked my stuff, put in a whatever, I don't remember whether it is a polythene bag or whatever I use, and I walked away. That's it. But I used to do duty up to 11 p.m. Some of them thought I was spying their school, that maybe they are leaking 11 exams or whatever. They thought I was a spy. But I was doing duty. Every time it reaches 5, I would get a desk, sit in front of the staff room, get a bunch of papers, students come, I chop numbers. When I'm on duty, I'll do it alone. Because one time I beat the whole class, the 2 students, 6-6. I got pain in my shoulder. From that day, when it is duty, I would do it alone and I wouldn't say any word. The school is quiet. Because I told them, my hobby is beating. If I find you making noise, you have fulfilled my hobby. And when I'm caning you, I want to cane you and you feel it. I want you to feel that I've caned you really. I've not caned a student for anybody for some time, and I don't think I can cane any student now. So sometimes they thought maybe I'm a soldier because of my character. But I don't, if you want to be like I am saying, you have to work hard. Even here, I don't give a damn. That's why I complain. These people are busy doing that stupid thing. Your timetable is done in a fake way. I am always here late in the night. When COVID came, I left. No one saw me around. I said, but where is he? He's no. I left. There's COVID. I don't have to be here. Soon I will say I'm tired now. I've taught enough. I have evidence. I've had videos. Anyone who wants to know how electromagnetism is explained can go on videos. And I will pack and do something else. You understand? I want to do, when I'm doing something, I want to do it with my heart. But when my heart is fed up, so that's the way I have been. So I hope this will be worked on. Today seems okay, but even if it wasn't okay, there is no colliding person today that would use the lab. The one who would have used the lab, maybe he will use another place, I don't know. I can talk to him for him and see, but he uses the other place. The reason I like him is because I have a key, being that I was in electronics and I've been a person in instrumentation. I have the key, so it becomes easy for me to, I don't know whether I need to give it in the door. None of you, so I don't know how you guys take life. I don't like the baganda. How do they call it? How is it said, the Margaret? Like people who want to squeeze you just for fun. I'm not that type. That's why I was very complaining of your lecture. Is what? Colleague. No, it's not my colleague. It's not my colleague. It's my workmate, but not my colleague. I don't think colleagues behave like that. You know, calling you and you tell me, that's just a party. These ones are doing assignment. It's not my colleague. Let me get back to you. But I apologize, don't take my words as if I'm having an issue. I don't have an issue with him. Actually, I've never talked to him at a personal level, like talking about something. We just met one time at a restaurant before this happened. Said hello. The talk is on the phone. But I'm pissed. Like, what? No, it is before this happened. It's before even his, I think he hadn't even defended his PhD. And when we met, I was trying to tell him that you can go to my channel and see the videos of PhDs I have recorded that can help you know how the defense goes. So, where are the others? Because I'm expecting 35, at least. They are still home.
We are waiting for an hour. Where we should be.
Supervising the mock.
They are still supervising the mock.
Yes.
And you? You what? You absconded or what? You don't give it down. No, you did not give it down. Jeremy, you have changed. You don't give it down. But I'm happy. I talked to Jeremy. see what I was looking at. So I wanna start on the course. I will go step by step. Try to make sure that I summarize the course according to this. So this is what they call yellow notes, when notes have started becoming yellowish. So if I had hope that I would be teaching for more years, I was going to write them, then seal them, and file them when they are sealed, each page. But I don't know. You don't know what I'm saying. You just have to. There is a sealing machine, like the one we use to seal IDs. So seal each page. How much? It's not about money. It's not about the money. It's about what you are doing. You know, these are the people you are putting on shoes, you reach mud, you remove the shoes, carry them into your hand, step in the mud, reach the other side, then cleanse your feet, put on shoes. Whether you got an infection on your feet during the mud, struggle through the mud, you don't care. Your shoes are okay. That's the stupidity of Africa. I'm an African too. Isn't that the logic you are saying? When you say it is too much money. Depends where you're going. Where I'm going, if I come when I'm muddy, everyone knows that it was raining. But my feet are okay. You laugh at me, but I am healthy. Instead of looking nice on the outside, but my feet are busy. Some whatever parasites are busy infesting my feet. So we start with those who were not there yesterday. We shall review electricity and magnetism until when we reach a point that we shall be looking at the Maxwell's equation. That's the beginning of the course. Whatever we shall be doing, we shall be starting from the review of electricity and magnetism. And we started from we take the journey of the charge. And this charge starts when it is stationary for electrostatics. When it starts moving, we get steady currents. When that steady current causes a magnetic field around it, we talk of magnetic fields. Then when we get more interested in the force produced by this current which was flowing in the conductor, we talk of the bias bar. Then we get the magnetic flux density nearby this. And then eventually get the amperes per kilowatt, know if we are within the region of the wire current. Look at the wire which is wound up to the solenoid, and then we get the magnetic flux density inside the solenoid, and then eventually cause this field or harness the field, produce electricity. We aren't going to go to the AC circuits in this course like we did in electricity and magnetism. But then we shall now harness. Instead of going to the AC circuits, we now harness the magnetic and electric field fields we would have produced, and then try to work around them and use them to transport some information. And that will be the part of electromagnetic wave propagation. And then we shall end up seeing the propagation in free space as well as in media, both conducting and non-conducting. And then we shall, if all goes well, I can try to introduce you to the transmission line. If it doesn't go well, then I let you read it on your own, the transmission line. And then in electronics and instrumentation, we shall look at the communication system. And then that will be from when we have transmitted our information, see the processes it goes through, and then afterwards, so we have a transducer, and then we have a receiver, and then we shall be able to see if I transmit, how do I make it in the medium across and then when it reaches, how do I make it resonate? So this camera here has a lens. I'm talking, the sound is going to the microphone. Eventually, we did this in electronics. But eventually, when I want now to play this video, I need a laptop, which is a hardware, so that I am able to see it. So if I'm on phone, when you are calling on phone, the other phone needs also to have a speaker. Here I have a microphone where I'm talking. Then the other one has to have a speaker where you get the voice, which is being spoken. So that's how we shall be able to. And I'm very excited that now I'm teaching these two courses together in a way to make sure that it is easier to relate. So let's start. You can now write. And so go to electrostatics. And we shall have the use of ozone, which you call poison, and Laplacian's equation or equations for solution of simple potential problems. Simple potential problems in Cartesian, spherical, and cylindrical. Currents. And whenever you got the potential and you have a surface, then you need to know, for example, when we look at an electric field is permitted through a medium. So if this is my medium and I'm having electric field lines going through this medium, then I need to know how they will be affected across the boundary. This is an interface. Interface means that space between two media. So if this is medium 1, this red book, and this other book here is medium 2, in between them here is what we call an interface, the boundary between these two surfaces. So because of that behavior, then we need to know what we call the boundary conditions. So we got the boundary conditions. For dielectric interfaces. So this is where you have to remember those dielectrics from electricity and magnetism, how we looked at how polarization takes place, how the electric displacement vector behaves when you are moving across the interface, across these two media, and that should be able to make you understand. So this makes me try to remind you of the Poisson and Lagrange. In this course, it is all about the electric field and the magnetic field. Sorry, it's B. Although these are the way we write them mainly, but these come from okay. This one is always related to this, but actually it should have been related to the H. So B is equal to UH, and E is related to the electric displacement vector as epsilon E. And these four are called, we shall be using the terminology field vectors. So whenever you meet a word field vectors, they mean the electric field intensity, magnetic field intensity, magnetic flux density, and electric displacement vector field. That's what we mean by the field vectors. And then we shall, in the electric part, or in an electricity part, we shall be looking at these two as the and how they are behaving at the boundary. And then when we go to the magnetic field part or the magnetism part, we look at these two and how they behave. At the boundary, example of the boundary which I innovated is the transformer. The transformer, those laminates will give us the boundary condition, understanding of the boundary conditions. For this one, we have the electrics, which we all know how they look like. So, why do we do this? Understanding is because the Gauss's law tells us about how we need to, what we need to be aware of when we are trying to diverge the electric field. So if you are diverging the electric field, then you must make sure that you are aware of the charge you have and how the medium around this charge, within which charge is placed, permits that charge to send its electric field. So here we have, of course, from the equation, the permittivity, the permittivity of that medium affects negatively the diverging of the electric field. The bigger the permittivity, then the more your diverging becomes a hassle. And the more you got a charge, the more you are going to be lucky to have your electric field going far away, reach a more place, a far away place. So the struggle is about how you can send. So if I can divulge a bit, the more money you have, the more you can make your relationship stronger. True or false? But it is a hassle. When you have money and you are not available, women will tell you, we can't eat money, money is not everything. When you don't have money and you are available, they say, do we eat love? So some of us get confused and are like, which one is which? You give the money, they say, but you are always not there. You give the love, say, but do we eat your love? I don't know. It's up to you. So it is from this that Poisson said that the minus grad V equals to E. And then he said that the divergence of minus grad V would be equal to rho of epsilon, implying that minus grad squared V would be equal to rho of epsilon. Therefore, grad squared V would be equal to minus rho of epsilon. And Poisson said, this is my equation. So I'm just revising the actual, that is the part of the course outline, but now I'm trying to make sure that we see what is all about these parts. And then this man, I will still not be satisfied with how he took things into his hands, matters into his hands. So this, he said, in regions where there is no charge, then you have no charge density. Therefore, this will be 0. And he comfortably owned it. But you will appreciate his greediness sooner or later. So also this one here, we shall use an example of a vacuum diode. A vacuum diode is more or less like these tubes here. You got a cathode here, you got a gas in here, you got an anode here. You produce electrons there. They ionize the gas in here. The gas glows, makes the fluorescent material to fluoresces and gives us light. So we shall be able to look at, if we had two plates, one plate being cathode, the other plate being an anode, and then plate and anode, and then we are having these electrons moving across the boundary, across the gap. Then we shall find out the potential in the middle and be able to understand how this one. Then we shall be able to look at the Langmuir child. I don't remember the spelling, Langmuir child equation under this example of the vacuum diode. And then that will be able to give us the pulsar. For Laplace, we shall be able to look at a case of if you have along the y and the x, and then you have electrodes, one electrode here, and if they are infinite, and then you have another electrode along the I think it should be another electrode along so these electrodes are going along the z infinitely, and then you have, so if this is at A and this is at B, and then you have these two connected by another electrode here, then we can, in the middle, we can find the potential in the middle here using this Laplacian equation. But we shall apply these two equations and make sure we get solution of simple potential problems in these three coordinates: Cartesian, spherical, and cylindrical. And that's the reason I'm carrying these things here. It's not a juju. That's why I'm carrying these things here. This one here, this one here. Rectangular is this room here. Fortunately, this is not like the lecture theater where everything is crooked. This is a perfect box. So if we got this as the z, we got this as the x, it doesn't matter. So don't cram that the one up is always z. No. That is if we got a fixed building like this one. But if this is my box, this is my Cartesian coordinates, if this was the z, this was the x, and this was the y, if I put it like this, z now is along this way. The x is along this way, and the y is along. If I put it like this, so it depends on where you are, and that's why we normally invested in having what we call a reference point. You've got to have a reference point in order to say what you are saying, otherwise you get lost. There should be a beginning. You are rich by the people who are around you. You are clever by the people who are around you. If they took you to Harvard, and you sit in their class, and then they're asking things, and everyone is saying, yeah, they're explaining the modeling of whatever, and then you are like, and if they took you to which university is down? I don't know. You know, those days we were the only university. I think by our time, the only university, we were the only university, upcoming university was Marara University, so we didn't care. But nowadays we got a lot of universities. So which university do you know that has dumb people? Cavendish. I don't think Cavendish, they offer physics. They have that. Anyhow, what I'm saying that if they took you to some place, I refused to go back to the village to teach in the village because I would rust. You reach there, you are the expert. You are the one who explained everything. Then in a few years, you now go to their level because you no longer have anything to explain. But here I'm challenged. You are explaining to somebody, he doesn't know, and maybe you are the expert, but he's argumentative, so you want to, on you, make sure that you can explain to them. The time when I used to do the actual moon viewing, I really used to see once in a while when my eye would pass, I would see curious people. So I would need to explain. One time I even had a moon viewing that was attended by diplomats only with their children. Whites only. Blacks were nowhere. So the examples I used to give, if you remember those things I used to say that Africans are stupid. We have every year is the same. Monday, Friday, January, December. Now I couldn't say those things too. Diplomat. So I needed to make sure I twist my language now to make sure I fit in them. And I don't insult them. So, the reference point is this. The reason people have problems is when they compare themselves with others. If you compare yourself with others, you die miserably. I don't. I run my race. Now I don't know if I was to compare myself, who else has this? You get my point? Either you will relax and say me, I'm okay because everyone is fair. So I don't go by other people's way of doing things. I do my things my way. And I don't care whether you say the man is making us suffer or whatever, that is your problem. When you become big next time, you want to come and appreciate, but you are very shy. Many students who hustle me up now can't meet me and say hello because they really feel bad that they mistreated me when I was giving them my best. So I want to explain the Cartesian. So Cartesian won't be too much of a problem. It will be normal, except that now in Cartesian we shall be talking about, most especially, I have wrapped the equations, but the key equation we are looking at is this and this. So this baby here is what is of essence. And so in Cartesian, we got the gradient operator being the same as Kali by Kali xi plus Kali by Kali yj plus Kali by Kali z. Okay. But you find somebody else, someone choosing x roof, y roof, and z roof. They are the same. Unit direction vector along the x roof, unit direction vector along the y roof, and unit direction vector along the z roof. Or you can use the ijk. And so when you take this one, that means you simply have the grand squared being the same as Kali squared by Kali x squared I plus Kali squared by Kali y squared. Do we have these ones here? Because you have squared it, that means you took the dot product, and then when you dot it's I, j, then k. When you dot them, they are orthogonal, and if they are orthogonal, meaning that they are perpendicular to each other all through. So with this is k, whatever. it's only the dot, the I, and the J, and the K that survives. Any other becomes, because the I, J, for example, will be the same as I roof, J roof, magnitude. Then since it is a dot product, we get the cosine of the angle between them. The cosine of 90 is 0. So is the IK or KI, whichever, because we know that A dot B is the same as B dot A, gives you the same. So you won't have any vectors. And this would be Kali by Kali Z. I mean Kali squared by Kali Z squared. So the Cartesian is okay, not much comes in. So we get to the spherical. And the spherical is the reason I brought this baby here. To make sure that you get to know how spherical works. And I hid the other weeks on wedding, but when I open the map, you'll be able to see the animations that explain this spherical thing. So spherical is like the Earth, and when we talk of the Earth, there is an equator, which is the part where when you slice the Earth in the middle, if you chop the orange in the middle, and then if you consider the Earth as a bulging balloon, when the balloon is bulging, the coordinate that will be changing at that point mainly will be the radius. If the other ones are changing, but the first thing to notice is that the radius is becoming. So for when we talk of the spherical coordinates, then we talk of, because the first coordinate is R. So, but let me draw it so that we get the feeling. So this is the center. So every time you are enlarging, so this is the zenith. This is the zenith here, the zenith. So if when the balloon is small, see, when the balloon is tiny, the radius which was bulging, when it's tiny it comes like, so when it starts bulging, you get this angle here, which we call the zenith, the theta. When you bake it big, it keeps, if you scratched on your balloon, assuming my head is a balloon, so if you made a dot on the balloon, and now you start pumping, the dot which was up here will start now going this way and enlarging. As it enlarges, you see the dot going this way. So this is how we get this angle here, there. Now if this is the equator, this is the plane of the equator. And because here on the diagram you don't feel it, I have it here. So if this is the, forget about this frame here. Is it frame or flame?
Frame.
Which one? Which of the two? Is it this or this one? Which one is it? This one.
Yes.
The frame. For us we say leptile sleeping holes. So this, forget about the frame and focus on this earth here. When I spin it, you see it properly. You see that it is a sphere by illusion. So this is the equator I'm talking about. When I spin this, so assuming this is a plane here, assuming you can put the film on this part. If I spin this like this, the angle chopped by this plane here, the vertical plane here, that angle here, which if we were to take this as the coordinate, and then we take this, so no, let me take this one as horizontal like this. So if this is the other coordinate, so this was Z, and then we have, you can say this is X, this is Y, and then so here we have the radius R, this angle here that sweeps this equator here is what we call phi. So this is the angle. So the spherical coordinates are r, theta, and phi. So r is when I blow in the gas, it enlarges, r increases, or when you reduce it, decreases. Then as you do that pumping in, as r increases, the angle also changes. And then when you sweep across the sphere, then the angle being swept by this plane eventually gives you the phi. And I forgot to bring the stand where it sits. This one I did it on the moon viewing. Did I do it in class? I've just repaired it, so if it pops out, don't laugh at me. It had enlarged, so I cut it to make sure that it fits on. And I told you that I can go to City Square and make magic, and people pay. just get nice dress, like a track shoot, some nice sneakers, and some good goggles. And the people will put money, and you will not be poor. So if it was spinning too much, this is how the earth spins. And this is how God made it spin and dropped it. So the equator is this flat part here I'm talking about. And this other part, this other plane here, which is chopping through the angle, this angle there, this angle here, that will eventually go out to 360. So so here is the deal. This angle, this radius here, the dot, when you are having a small balloon, the dot could have been on top of the balloon like here. You can pump it, the much that it can do is to move and go up to here. If your concern is about, if you had a charge here in the middle, and then you are having this charge giving out the electric field, this electric field can only be experienced once on this part here. You cannot say that I'm now going back this side up to here. So that means that the R ranges between 0 and pi. No, sorry. I am sorry. I'm sorry. This should be able to bulge up to infinity. I'm talking about this angle here. So R will go up to infinity, but it starts from 0. Sorry about that. And then for theta, I've already explained it and knowing. So this will go up to, and then the angle here, swept, you can sweep it from when you have 0 up to. So this will be 5 up to 2. And then you now know everything about spherical coordinates. Once you know how each of the coordinates behaves, how it is related to the other coordinates, and also the range. If you are doing integral, because at the end of the day when we are doing integral, then you'll be knowing you are integrating from where to where. So the reason this angle here, I'm sorry to have confused you. This angle you can only move up the angle of 180 here. When you cross, you meet the same field lines with the same properties as you have already covered. Anyone having issues with the Cartesian coordinates and now spherical coordinates? So the next one is the cylindrical. So when I took water from my bottle, I made sure I saved it. I don't throw away stuff, so my house and my office is dirty. Sometimes the cleaner comes, wants to clean everything, then I quarrel. I have a magnetic stone which had the iron filings on it. She came and cleaned it. It's now naked. My magnetic stone now is naked. She cleaned everything. So very interesting. I don't know what to do. Me, that's why I told you I want to be a lion. People want to be clean. Even you throw away things that are important just because they want to be clean. So for what? I find it very difficult to throw away anything. And after some time, I find it very useful. I had, let me tell you this, maybe you may understand what I'm talking about. I had a LED light which has a USB. You just plug in a USB, it has a flexible handle. And then I had the modem those days, which also had a seating USB port. But that USB port was useless those days. Then I bought this LED thing, also it looked like it is useless because you had to first plug it in, and then the only light can be just up to the keyboard. Now one time as I looked at this thing which can sit down, and then this LED thing I can plug it in and now make a small reading table lamp. That is a bit more fashionable. Had I thrown out all that stuff, I wouldn't be able to do that. So I don't throw away things. So I made, in one of the boxes, my packaging boxes, I made this, so consider I told you I don't throw away things. Some of the things are in here, I don't even understand how to find batteries. Okay. So this, if you consider glass, juice glass. So we got a juice glass, but I will make sure the glass is uniform in terms of the I don't know whether circumference or whatever. So this glass here, if it starts as a tiny glass, if you could make it a tiny glass, like how these balloons on these longitudinal balloons which they put on functions. If it is tiny, it is small. So as you try to enlarge it, so this distance here, this distance from here to here is what we call R. In some literature, we call it, some literature you find that it is called rho. Some books. On the spherical, R sometimes is called S. So, especially when you go to this book, the introduction to electrodynamics, and then you go to the identities. When you go to the identities here, you will find that instead of R, some of the parameters are S. These parameters here, I think this one is having them at the beginning. These parameters here are Laplacian, spherical, Cartesian, and cylindrical. Some people you find they have used rho instead of R. Others use S instead of R. So don't be confused. He talked about R, and now here I am seeing S. It's the choice. Some people just write things in a complicated way to make your life hard, or to show that they studied. Now, if we just put here some coordinates also, x, Y, and then Z here. The level as the juice. So consider this this line here, this plane here to be the level of the juice. So as the juice increases, as I pour juice, as I drink, as I add in or drink to reduce it, I'll be changing the Z. Okay? As the glass becomes bigger and bigger, that is the R. So we have the R, we have the Z, or we first, I don't know whether the arrangement is that the Z is the end, is at the end. Is the Z at the end or is this 5? It's the Z which is at the end. Okay, so now, if you had a plane, this plane here, and that plane is sweeping through the glass, like if you had a blender which is mixing the juice, that angle it takes for one spin or whatever, that plane here sweeps the angle, this angle. So if this is the R here, and then we take this plane here, which is, if we had drawn it nicely, this plane goes here. So if this plane here sweeps through the angle, sweeps through this angle here, down, R is there, then we have the coordinates. We have the X down here, going down, and then we have this is the X, this is the Y, and then the angle being swept through is the phi. And so we shall have this angle here swept by this plane here, and then across this bottom here will be our phi. So it will be phi and C. And so, just like we say, you can have your glass up to infinity, from 0 here. So, and then R also can go up to infinity. You can make it bigger, so you have 0, R, infinity, 0, then phi goes to 360, 2 pi, and then Z goes to infinity. I didn't buy nothing, maybe these ones. But this one, so one time I told you the story of one lady who was teaching us math methods, and then she said, you can be innovative. You can tell your children to go out of the class, go to the compound, pick the polos, then use some threads, and then you tell them to wrap the thread around as an activity, then they measure the length, and then you tell them how they can relate the length, so which of course was the circumference, relate it to the diameter, find the area. So she said, if you have any comments, you can come to my office after, and then so I went to her office. So I asked her, if I'm teaching in a school like Vienna, how the hell do I take people's children in dirt that they are collecting garbage, if there is garbage anyway? What if they get an infection? And she looked at me. I've been a problem to many of my teachers. I think God said, you have been a nuisance, you go and become a teacher. I think that's what God said. That's what I realized. He said, you are a nuisance, go and become a teacher and face the trouble that you give people. She didn't have anything to say. You don't tell me to start, of recent, one of our, let me call her a colleague from music, wrote a project that they want to use music to encourage students to learn mathematics. that you go to class, then you first tell them to sing. After singing a song, then they even got a playlist of songs that can rhyme in the mathematical, whether I don't know whether you do rather than. Me, I told her point blank, I said that's nonsense. I go to class, yes, you ate money of research, you are rich now, but it is useless. I go to class to teach, I got 45 minutes. I cannot waste even 5 minutes that I'm making people warm up, that they are doing exercise and singing. I'm not a singer, I'm a mathematician. But I challenged them. They are in music, dance and drama. A movie is a novel. Most thrilling movies are a novel. They make it a play and it becomes a movie. What does VJ Jingles do? He comes and, can you imagine VJing a Luganda movie? The movie is already in Uganda. And VJ Jingle is already talking in a Uganda movie. What kind of nonsense is that? Adding hype. What is that? In a movie. So instead of them going for their own field and make it perfect, they are jumping on mathematics, which they had no idea about.
And they are all music after failing mathematics.
Yes, after saying math is hard, they went there. So where there is a fundamental problem. Everyone thinks that anything is an innovation. No. You fail to tame gene. You can imagine, you can make one woman tried it and it worked. This woman of NTV, she was, I think, Conde. Agi Conde. She actually made the Salvador movie, and they played it now in Uganda. And they tried. They reacted it. But you just get a bunch of people, train them on voice, and make sure that they can translate all these soap operas. But if I became president, I would ban all the Latino, those Musanyo. They have spoiled our women. They think that now they can play games around, you know? And I would ban them completely. If I find you watching it, we put you on a firing squad.
That's why we continue.
Okay, so anyone with an issue, on this, I'm very radical, because you find these women, they are driving home, going home just to watch. If they don't, they feel bad. They're asking a friend, what was it today? How did it go on the phone? And it is all about, how can I call it? It's an illusion. They will show you a big bungalow, the best vehicle, they are gifting each other vehicles, and then we have poor men now being corrupt just to satisfy their stupid women. And let me tell you, ladies who are here, you are the problem why corruption is flourishing. If I buy you a nice necklace, and I am just an accountant, where the hell did I get the money? And you are like, hey, thank you, honey. And you know I have screwed up people who have gotten services, and for you are having all the money here in your neck. And you move around. Huh?
It is also one kind of corruption. You have to first give and they accept. That is corruption.
That one is normal. It is Adam who goes wrong. But I find it, look at the men they have gotten in corruption cases. Their women are living large and they don't care. Anyway, I live in my own world, I think. Is there any woman who can ask her husband that, where did you guy comes and brings you a Range Rover. He's like, honey, here is you. And you are like, can't you ask where do you get this money? So I made the research and asked my female friends. I said, why are you always accepting to be lied to? A guy, if you met, if I told Nabonde that that new mall near Mapera is mine, she will accept. She will not bother, she will not start quarreling with me. So I asked why. They told me, we know that the person is lying, but at least he has ambitions of getting that he has ambitions of getting big things. Yes? He knew where she was stealing the money from. So that one is a case no. He knew where the budget, where she was. I don't want to go there because there is a bad mood for me to go in that direction. Being managed by a former house girl is very, very bad. And then, anyway. So that is about the other bit of boundary conditions. We shall be able to get back so this outline is not so big. We have 4 to 5, we have 5 to 6, and 6 to 7. There is nobody who is going to teach you those times. And that's why I'm taking my time to make sure that I finish the course in this time. You have what? You have practicals. From 5 to 7? Yes. Who teaches it? You tell him BFP has said us. I have no problem. I have no problem. I have my time. I have my time. You can give all the excuses you want. I got a time. I got a content. 2. So I wanted mainly to demonstrate to you Cartesian, spherical, and ceramics. So now we set the charge in motion, and then we talk about stationary electric fields and conducting media. So here we look at the conductors because it is in conductors where the current flows. We call it stationary stationary electric field because when the current is flowing continuously, the electric field lines are stationary. They seem like nothing much is changing. So here we look at the conservation of charge. Conservation of charge. So charge is neither created nor destroyed. Just transforms it from isolating a negative charge from a positive charge, making a positive material and a positive material or current too, and then they rise and you get more charge. But it will be there. You haven't destroyed it. So conservation of charge and continuity equation. Then electric fields in conductors. Electric fields in conductors. Then we have calculation of resistance of coaxial cable. Calculation of resistance Then we look at army closets. Army closets and power conservation. These are just terminologies I use here. They can vary, they can be the same. So I just want to explain the conservation of charge. I've already talked about it. And then the continuity equation. The continuity equation is that if I got a charge and then I put it in my volume. This is my volume. So I have each charge in my volume, and this volume, I take a small surface here, small surface, and then I look at the charge which is escaping from this volume. So as the charge escapes from the volume, that charge, as it pierces through the surface to go out, this is the surface bounding the volume, and this is the volume rho. So the charge density in here is the rho, and then you have the surface S, and then you have this is the one of the current density field lines emerging out, and then you have this one. And so we know that the charge flow will be from positive, and where it is going is the negative. And as the charge is leaving, this surface is where we talked of the Q is equal to rho d tau, then the current is equal to minus dq dt, and at the end of the day we say that as you diverge the current density, this current density, as it diverges out of the surface, then that should be related to how much charge you are losing from the surface. And this charge, the rate at which you are losing this charge, is what we call, so this divergence would be the same as the loss at the rate at which you are losing the charge. The rate is this Kali by Kali T. And the charge we are talking about is the charge density. And this is the equation of continuity. But of course you start from the bit of the rho d tau. Then you have also I equaling to minus dq dt. The minus is that you got the loss, you are losing the charges being lost. And then you bring in the idea of the I being equal to minus d dt of the integral rho d tau. And then you have the I equal to minus Kali rho by Kali t, then the tau, EDC. So I don't want to go to the derivations now, I just wanted to explain the physical understanding of when the charge is being lost that constituted the current density, eventually makes you understand the equation of continuity. Then we shall calculate the resistance, and then we shall talk about the coaxial cable because of this banana cable here. So because we were not there yesterday, these banana cables are very interesting. That they are female and male. This is a male. This is a female. Don't report me to the sexual harassment committee that I was showing how the male is attached to the female, whatever. So the coaxial cable is this part here. We may draw a big cylinder going across and then an electric, but this is a sample of a coaxial cable. You have the outside cylinder here, inside the cylinder, and then you have an electric in the middle. And then we shall be able to look at the resistance, the impedance of this part here when we reach the electromagnetic waves, Z, should be about 377 ohms once we do the calculation. If it is going to be able to make sure that it does not affect our signal when we are using it. And that's why you see these cables looking the same, almost same distance here, almost, so that all those properties are remain. And then of course, ohmic law said, then power conservation, just to make sure that so we are trying to learn these to make sure that when we now start understanding how electric field lines are, electromagnetic waves are propagated, we know the media we are going to use. If we are using this media, then we know. If we are using wireless, then we know. That's why when it is raining, you get those boxes forming up in the satellite TV nowadays, because you are now affecting the medium across. You start getting images getting stuck when it is raining because of the medium has changed. Three, we now look at this charge. The current that has been flowing here, we see how it produces the magnetism. So 3, we look at the magnetic field lines, magnetic field laws. Magnetic field laws. And under these magnetic field laws, we look at the circulation, and flux laws. On the magnetic flux density B, then we look at the forces and the torques. Forces and torques on current loops. Then that transforms us to induced EMF. Which I didn't come with a coil today. Induced EMF, because we did it in the electromagnetism. Then this one is more explained by Faraday's law. The more the speed, the more the excitement, the more the induction, the less the speed, the less the induction. And that is the dphi dt. And then go to mutual induction. We don't care about self-induction. The reason we talk of mutual induction is that whenever you have two coils, the coil A will affect coil B, and that is the basis of cellular telecommunication. And that will be more explained under the Newman's formula. And then we shall get something beautiful called the magnetic vector potential. Just like we talk of the vectors and scalars in the electric fields, the scalar potential grad V equal to electric field intensity. Here we talk of the magnetic flux, magnetic vector potential and magnetic. So the magnetic vector potential, and then finally we look at the electromagnetic induction. Electromagnetic induction. So under this circulation, we look at got a wire, got a cardboard, and when he got a cardboard, he made this wire to go through this cardboard, and then so he poured everything here, the iron filings, and then he switched on the current. Of course, when I do this, it's like if I did this, and then there is a switch here, switch S. So he switched on the current. When the current started flowing on shaking the cardboard, then these were able to arrange themselves in concentric circles using a small compass and moving it along those outlines of the concentric formations. It was discovered that the north of the compass was continuously pointing in a given direction. That's what was found out. And that showed that you can use the right hand grip rule, and if your thumb is in the direction of the current, that field direction will be in that direction. I have a small theory. Once I have drawn my current, I just say right is right, and I put the arrows, and then I will complete my field lines, and then my arrows comfortable. You can use a corkscrew. You can use the arrow ball. If you are seeing the arrow, that's a dot. So this is the dot, and this is the cross. And if you were having the current going down, this would be the cross for the screw. And if there was screw, if you are in the radio and they are screwing up the radio, then you will be seeing a dot here. If you are the screwer, you'll be seeing a cross. If you are tightening, so that means this one will be like this. So this arrow will be going that way because you are screwing, you are tightening. If you are covering the cork of the flask, you can imagine I have never seen a flask when I was young, and someone is explaining that when you are corking up this flask, I don't know the flask for what? For us, flask for what? Just make porridge, you put in a big pot, it ferments, you drink anytime you want. These people who say, there's no water in the fridge, for what? You just go with a calabash, a half calabash. You know calabash? We split the calabash for us, like this. And then this whole thing you dip in the porridge and gallop. I missed that life. No hustle. From school I gallop like 4. Then I go in my books. Here you come from, you are coming from class, the posho is almost gone. Then you have just eaten the posho, you are supposed to be dosing. No water. The water they give you is hot. It is not even cold. For us who started from home and enjoy life, you just have fun. Eat anything you want. But I used to like the posho, which is the one which is almost towards the bottom, the one which is almost burnt. And the teacher, the food master thought maybe at home we don't eat, because I would have eaten potato, I would have eaten pumpkin, everything. But that posho down there is the way it had a taste, that smell. Then when I came here, the posho here used to be like as if they have just smashed it in the water and put for me. It was boring when I reached here. Even when I eat at the restaurant, you reach there, it's like, it is not posho. Posho is that burnt thing down there. Because at home, if they would make that porridge, that sorghum, whether posho, I don't know how they call it. There's a way it gets burnt also.
Yes.
And if you leave the saucepan to cool down, you remove that chapat down. So I don't know what the Gen Z really, what they find as a delicacy. For us, for me, I enjoy it like. So when people see me, they think I'm a pizza guy, a guy who knows about pizza and these things. I am marinating chicken. You eat chicken, but you are eating wheat. The whole most part of it is wheat you are eating. The chicken is just So the magnetic flux density, and then the forces, the torques and the forces, I will not waste my time. This is medical stuff, okay? It's, in the Navy we can talk about it in electronics and instrumentation to show you how instruments are formed. In induced EMF, really, you know these things now. You know Lenz's law, you know Faraday's law, the mutual induction. It's going to help us on the Newman's formula when we have two coils, and then when you change the current here, it produces a field, changing the field. Now you use a current here. So this is phone 1, and this is phone 2. And then you are able to communicate. That's how cellular phone was discovered. The mobile phone, that's how it was discovered. That I have a coil here, I produce a field. The issue of encryption to now make sure before you put airtime you can't get. Just like now the TV, you can't watch TV if you don't have, if you are not subscribed. And I dumped their decoder. I use free to air, and I'm going to make my next movie is now to make some small short videos to explain to people to dump their decoders and buy LED TVs, flat TVs. For the internet, I succeeded. MTN screwed me up, changed my monthly payment to bundles. I made sure I give this place internet. Now it has even become worse for them. Internet is even in the toilet. Now, so MTN cannot make a single coin here. Can you activate your ban when you are here? So I managed to. Unfortunately, it is going almost in every university. Every room is going in every university, so they will not pick any coin there. Now, when you are on Star Times, even if free to air, you cannot access when your subscription goes. But when I'm using my free to air, if I am using this like the TV I have in my office, I just put an antenna, that's it. I get free to air channels. So I'm going to campaign people to throw away their decoders, buy these TV, because when you calculate the money you spend, 30,000 per month, in a year, you have already bought the flat TV of 300 something, 300,000. 350 you buy a 32 flat TV, no subscription. I don't want people who cheat others. I don't like it. We are not here to be cheated. We are here to be served and given services. So then the magnetic vector potential and then the pneumatic induction is almost this other part here. 4 is the beginning of the course. The number 4 we are going on now is the beginning of the course. This one is just to understand a few things. This is just about trying to make sure that we know how an electric field and a magnetic field behaves, how it is affected, how it is produced, how it is enhanced. Because here when we are doing electromagnetic induction, we are producing electricity. Meaning that we can sustainably, if the water in Jagali or in Karuma is flowing, you are sure of the electricity. 24/7, all the time. As long as the turbines are running, electricity will be flowing. That means if you wanted to use that electricity for anything, then it is available. That's why we have been understanding this. to make sure that we can sustain an electric field. And then Maxwell comes in and then does amazing stuff with this electric and magnetic fields. So we look at the derivation of the four equations and then the displacement current, then equations and solutions in terms of the electromagnetic waves. Equations and solutions in terms of electromagnetic waves. And these, we look at the free space, and then the transverse nature, of electromagnetic waves. I'm cutting it short, EM waves. Then orthogonality of the electric, of the magnetic, and the propagation vector. When we have I'm the only one in the world who can do this. I did it in electricity and magnetism or not. I'm the only one who can demonstrate with my bare hands how the electric and how the magnetic component propagate together. Then I make them move in this form. So they go like this. I'm the only one who can do this with confidence. It's trying, you can't. I'm the only one who can do this. This one is horizontal, this one is vertical. So we go. And when they are reflected, this one I'm still learning. They are still reflected backwards. Got you. So you're struggling to see how Mustafa is saying. Mustafa, it is just as simple as this. This one they start. This one is going. This one is coming up. So. And they can even be quick. You will struggle in your own free time. So we look at the derivation of the four equations. We diverge the electric field. It would be the same as diverging the electric displacement vector, which would now be just equal to rho. If we had to put E here, this is epsilon E, then epsilon will be down here.
Yes.
Then the next one is to do the same for the magnetic field lines. You diverge them, they disappear. You curl the electric field lines, you can only manage to maintain them available the moment you make sure that you continue cutting through the magnetic field and the electromagnetic induction, which we finish. 4, you try to curl the magnetic fields, then you must make sure that you have the current density and also the way the electric displacement vector is changing. And these are the four Maxwell's equations. Once you count this one and this one, then you get the EM waves. And you prove that these move at the speed of light. The video is there when I'm doing this. Those who want to do it now, I have no time. I need to finish the write-up of the course outline. Then, so equations and solutions in terms of electromagnetic waves in free space, where we end up there by doing that, and then the orthogonality is that as I have demonstrated, when this is happening, this directional propagation is the K. But if you cross these two, E cross B, you get what we call the Poynting's vector. And that's the heat you feel when you put your hand on the sunlight. The heat you feel is this energy per unit. This is the energy per unit area. Or you can say it is the energy. What do we call per unit area? What do we use? Flux. When we say electric flux, we are looking at the amount of electric field lines in an area. When we talk of the magnetic flux, we are looking at how many magnetic field lines are heading in an area. So I'm done with this. You now have an idea on this number 4. So I want to make sure that when you go to secondary and you're teaching electrical magnetism, you chop the whole liquid and throw it there. And tell them you can now go and discover things. That's the resolution I made when that teacher who came and said, "Come and go to Makerere." I got annoyed. I said, when I become a teacher, I want to chop everything. And then the students can go further. Why do you become mean to students? You just chop little, then they also struggle to chop what is there. What is the use of that? Chop everything. And then tell them you go now and wonder. Don't be mean. 5. Polarization of electromagnetic waves. We will do this more in the optics. Polarization of electromagnetic waves and microwaves and fiber optics. Then we have linear, circular, and elliptical. Linear, circular, and elliptical propagation. Sorry, polarization. This is polarization of electromagnetic waves. We had polarization of meridians when we made them acquire a given polarity. Remember our dance where we would all do lingala or whatever, and then when they put slope, the boys pocket and bounce this way, and then the girls start to walk, rolling their eyes. And then they sit this way, and then the potential is created across the platform, and it is a struggle. Only the boys who mime around and play football. For us, I was just lucky that I was an artist. So if you pose around me, you come to me to write for you on the card. So I also get you. Revenge. But we were miserable. It always in books. So the footballers and the mimers and the girls are just winning. They are pretending just to see, is he going to take a name? And then they grab. So for us, we just continue seeing the potential going down, until when there are also those who are now asking, can't we get somebody to get us? I'll not tell you the story. How our source ended. So this one you will mostly struggle in whatever, but the only thing I want to talk about is if the slit in a cardboard is vertical, it is only this one which will go through. This one which I have been doing like this, it will knock here and it won't go through. So this would be plain polarized. So the only vertical one has gone through. That is linear. Or if it was horizontal, if the slit is horizontal, this one will go through. This one will knock the cardboard. So it would also have been. Then you have circular. If you have a circular bit, then you have that bit going through elliptical. When it is elliptical, not circular, those things will be more in optics and whatever. Microwaves and fiber optics. Then, so you said your lecture starts at what time? Who does it? Who does the course? No. The students. All of you means
Both minors and majors.
and some other like statistics and what?
Yeah.
So it is a big class. So you can't notice that you're not there. Hey, you see how I'm trying to Poynting's vector, you like and you will. Poynting's vector in free space. Poynting's vector in free space. So we have a plane electromagnetic wave, plane electromagnetic wave, plane electromagnetic wave, waves in matter, isotropic. You remember isotropic, homogeneous, and linear? Homogeneous and linear media. And linear media. Solutions of wave equations. Solutions of wave equations in connecting and non-connecting media. So the new curriculum, this was my curriculum. This we would end here for this new curriculum, according to the new curriculum here, the book. The book would make us end here, but in a new curriculum, the last bit would be electromagnetic waves. Then the next one would be generation. Then electromagnetic waves in conducting media, reflection, inflection of the plane surface. Then the generation of electromagnetic waves, that is retarded potentials and electric dipole radiation. But our times, we studied transmission line, guided waves, transverse electric, transverse magnetic. Then wave guide as a high pass and a low pass. And then radiation of electromagnetic waves, that is retarded potential, which is hinted a little bit here. And then the two books are this Introduction to Electrodynamics by J. Griffith, This is the key book. You have to read it page 1 to the last page. If you want to pass the course, this whole book, just like you were supposed to read Brophy to enjoy electronics. But you can always relax in free time on these distance materials by Professor EJKB Banda with a couple of some worked out examples, but all these notes are the same as the notes I will be teaching you. This outline is online. The parts I haven't written on the board. The actual syllabus of the new curriculum in interactive version is also on Mwele. I have created course resources, a link. I am creating a web page on Mwele with all sorts of things that I would love you to access. Links, videos, whatever. So I have called it Course Resources 2024. It's a link. It's a link like how you see those notes. So I want to make that one as a resource. Everything that I think is important for this course and for your life, I'm going to put it there. Just to conclude, this Poynting's vector is the heat you feel when you put your cursor down, put your hand on that light. How do you feel? Some warmth. That warmth is the S. S equals to E cross, and this is from the orthogonality of the E, the H, or the P, and then you have, the E is here, and then this is the S. So this cross product is the one which gives you energy flux. That is the heat you feel. And when you look at some of the classes, like in the lecture theater, you find the rest of the place is dusty, but that central part is not dusty. That means that has energy even to knock off the dust particles away from its way. It carries energy. And so, if you are innovative, you can look at how you can utilize that energy for something. Those who are in solar, they are trying to do a concentrator to make sure they can reflect that energy to a central point and do the cooking. Okay, so any questions? So I have confidently finished the course. Is there anything I haven't talked about? Which one?
And stuff with
This man is but you have a gym in enrolled. Is that on this fella? You have a enrolled. The only people who have enrolled is Chivira Ango, is Nani, is and then Kauma, then Farasida. And even Isekawa has not, but he sent me a message in a holiday saying hi, but he can't enroll the course. That's how some things are strange to me. At times I don't understand the magic behind. So we meet tomorrow at those who would wish to take electronics and instrumentation. We meet tomorrow at 8. This is very venue. And then we see how to move forward. Make sure you have registered. So I need my registration. You have, Fred, you have something?
Yes.
Yes.
That is just.
Then?
That is just to take electronics.
The what?
That is just to take electronics and
I encourage you. My young man. Yesterday you attended my lecture. I told people, those who were not there yesterday, that when I used to meet the students in first year, I would tell them, those who are doing BSc, work hard, it is a second chance. So when I was organizing the party, one of the students said, when I said, what don't you like about me? He said, the way you talk to us, that we are doing the flat course, that we need to have. Then I told the people that I'm not your father to switch talk you. I tell you the truth, then you choose how to do it. I'm not your father, so I'm not your father to convince you. Anyway, electronics and instrumentation is application of sensors, an application of sensors in electronics. So it's an extension of the electronics course. I want you to go to the mathematics. I don't want to be a cause of your delay. I'm done. At least I have finished my content. See you tomorrow. Those who want to do electronics and instrumentation. I have no time to interest you. Come if you want. If you don't want, you leave. It's a nice course.